FastMCP 2 employs dependency injection as its primary mechanism for providing runtime context to tools, enabling clean separation between client-facing parameters and internal execution requirements. This pattern allows functions to declare dependencies through type annotations or explicit dependency providers, with the framework automatically resolving and injecting these values at runtime. We will examine two equivalent approaches for accessing the context object within a tool: implicit injection via type annotation and explicit injection using the CurrentContext dependency provider. Both methods demonstrate how FastMCP maintains clean function signatures while providing access to request-scoped capabilities like logging and progress reporting. From FastMCP, import FastMCP. From FastMCP server context, import context. MCP equals FastMCP demo. At MCP, tool. Async def process data, SDR CTX, context SDR. Await CTX infof processing, data. Return done. Hash or explicitly with CurrentContext. From FastMCP dependencies, import CurrentContext. At MCP, tool. Async def process data, SDR CTX, context equals CurrentContext SDR. This code demonstrates two equivalent approaches for accessing the MCP context in FastMCP tools, showcasing the framework's dependency injection system. The first approach uses type annotation with context, where FastMCP automatically recognizes the parameter type and injects the appropriate context object. This is the more concise method, relying on FastMCP's built-in type resolution. The second approach explicitly uses CurrentContext as a default parameter value, making the dependency injection mechanism more visible in the function signature. Both methods achieve the same result, providing access to MCP capabilities like logging through the context object. The choice between these approaches represents a trade-off between brevity and explicitness. Type annotation is cleaner and requires less code, but the explicit CurrentContext makes the dependency injection pattern more obvious to readers unfamiliar with FastMCP's conventions. Both methods maintain the same behavior. The context parameter is automatically excluded from the MCP schema visible to clients, and the context remains request-scoped. The async nature of context methods necessitates that tool functions be async as well, which both examples properly implement. From a production perspective, either approach is valid since they're functionally identical. The type annotation method is generally preferred for its conciseness, while the explicit version might be better for documentation purposes or when working in teams where making dependencies visible is valued. Both maintain the same request-scoped context behavior and automatic schema exclusion that are fundamental to FastMCP's design. Let's break it down. From FastMCP, import FastMCP. Imports the FastMCP class from the FastMCP module, which is the main class for creating MCP model context protocol server instances. This import alone doesn't create any server instance or perform any operation. It just makes the FastMCP class available for use in the current module. From FastMCP server context, import context. Imports the context class from the FastMCP server context module, providing access to MCP session capabilities like logging, progress reporting, and resource management within FastMCP tools and components. MCP equals FastMCP demo. Creates a FastMCP instance with the server identifier demo. The string parameter serves as a label for the server that will appear in MCP protocol handshakes, allowing clients to identify this specific server instance. At MCP, tool. Async def process data, SDR CTX, context SDR. defines an asynchronous function named processData decorated with @MCP tool, indicating it's registered as an MCP tool. The function takes a string parameter data and a context object CTX, returning a string. The decorator automatically handles tool registration, using the function name as the tool name and generating input schema from the type annotations. Await CTX infof processing data. Sends an informational log message to the client via the MCP context, displaying the current processing status with the provided data. The await indicates this is an asynchronous operation that yields control until the logging completes. The message format shows processing, followed by the string representation of the data variable. Return done. Returns the string literal done as the result of the function execution. Hash or explicitly with CurrentContext. From FastMCP dependencies, import CurrentContext. Imports the CurrentContext class from the FastMCP dependencies module, which provides access to the MCP context for interacting with session-specific capabilities like logging and resource management. @MCP tool. Async def process data, SDR CTX. Context equals CurrentContext SDR. Defines an asynchronous function named processData decorated with @MCP tool, indicating it's registered as an MCP tool. The function takes a string parameter data and an optional CTX parameter of type context that defaults to CurrentContext, providing access to MCP session capabilities during execution. The function is declared to return a string. FastMCP2's dependency injection system provides two clean approaches for accessing the context object in tools, both maintaining the framework separation between client-facing parameters and internal execution requirements. The type annotation method, CTX, context, offers brevity by leveraging FastMCP's built-in type resolution, while the explicit CurrentContext approach makes the dependency injection pattern more visible in the function signature. Both methods achieve identical behavior automatic context injection at runtime, request-scoped context lifetime, and exclusion from the client-visible MCP schema. The choice between them represents a trade-off between conciseness and explicitness, with the type annotation being generally preferred for production code and the explicit version potentially better for documentation or team contexts where making dependencies visible is valued. This dual approach demonstrates FastMCP's flexibility in accommodating different coding styles while maintaining consistent behavior across implementations.
The context materializes to whisper logs, then vanishes, leaving only echoes in the request void.